Today's AP Stat lesson is going to do two different types of problems. One of the handouts is this guy right here, a little bit challenging to read with the focus of this particular camera, but basically what we look at is a different type of problem of calculating a least squares regression line. The information we're going to be given to start with is going to be different than what we've seen in the past. And then the other thing we're going to talk about is an influential data point, which is going to be the other handout. So those are our two objectives for today. We're starting with the first one here. So what's on this handout? Gives a definition of what a least squares regression line is. The least squares regression line of y on x is the line that makes the sum of all the squared vertical distances and the data points from the line as small as possible. Okay, a couple of important reminders here. Least squares regression line, that LSRL, that's an acceptable abbreviation in the AP Stat world. That stands for this. And the idea here is if you're talking about a generic term of a line of best fit, there are different algorithms that can produce curves for data or a line for data. Okay, one particular strategy or one particular algorithm uses least squares regression, and that's the type that we use in this class, so that's why it has that name and a reminder of the abbreviation. Okay, correlation. We've been talking about that for a little while now. Sometimes it's called the correlation coefficient. Sometimes it's just called correlation. Okay, this is the formula of where it comes from. So what your calculator does when it produces the R value is it is going to take the X list, find the mean, standard deviation, take the Y list, find the mean, the standard deviation. Then it's going to do these Z scores for each number in each list, multiply them, sum them all up, and then divide by the n minus 1 or multiply by 1 over n minus 1. Okay, so that's what's happening in the background in your calculator when you do a line of best fit. Okay, that particular formula is provided on your reference sheet. So this is the reference sheet you'll have for the 2021 AP exam. And I've highlighted in yellow the ones that are relevant to chapters 3 and 12. Okay, so that is one of the formulas given right here. Now it's highly unlikely that you are going to need to actually use that formula in its raw form, but there are times where knowing the structure of that formula can help you answer other questions. For example, a common multiple choice question that involves correlation, which of the following is true, which of the following is false, about correlation. And one of the things that tends to be in there is switching the explanatory variable and the response variable. Does that change the correlation? Well, switching the x's and y's, well, whether it's the first one times the second one or the second one times the first one, in terms of switching these two, adding them up, it's going to be the same thing. So although you may not have to use this formula as is to produce an R value, having access to this formula can help you address other things like I just mentioned. Okay, now on to the bottom. Try to raise it up a little bit. If you get too close, it doesn't make it any better in terms of the blur factor. Okay, we have data on an explanatory variable x and a response variable y for n individuals. From the data, calculate the means, x bar, y bar, and the standard deviations, s sub x, s sub y, of the two variables and their correlation R. The least squares regression line is. Well, we certainly are familiar with this format. Y hat is equal to a plus bx. Okay, well, it turns out that that slope uses that R along with the standard deviations of the x's and the y's. The other thing that's true is that we know that that line of best fit is always going to pass through x bar, y bar, or the average of the x's, average of the y's. Okay, the way that appears on your reference sheet in terms of remembering it, they flat out tell you there the slope is the r times the standard deviation of the y's over the standard deviations of the x's. And these two in combination tell you the other two facts. That, well, that's the form of line of best fit that we use here, and that y bar x bar, meaning that's a pair of values that solve that equation. In other words, then the line of best fit will pass through the average of the x's, average of the y's. So, what type of question would you typically see on the AP exam? Researchers recorded facts about 77 breakfast cereals, including calories and sugar content in grams. The following measurements were obtained. So they're giving us average of the y's, standard deviation of the y's, average of the x's, standard deviation of the x's. What the correlation is. Calculate the least squares regression line, calculate and interpret the coefficient of determination. Alright, so I'll recopy this bigger so it's easier to see. I apologize again. This particular camera I'm using does not do well with the small fonts. Okay, y bar is equal to 107. S sub y, 19.5. And we'll worry about the units later. They're on the sheet. 7. S sub x is equal to 4.4. Oh, we need an R too. I guess it is worthy to mention, as a reminder, well, when we're doing lines of best fit in the context of word problems, like we do with 99% of our stuff here, x's and y's clearly have labels. In this case, we're talking calories and grams. R does not have a unit. There is no unit associated with R. Again, another one of those questions that tends to pop up. What's true, what's not true about the correlation. Correlation has no units. All right, so we know we want a final answer in the form of y hat is equal to a plus bx. That b is our slope. That b comes from r sy over sx. Well, they told us r. They told us sy. They told us sx. So that's going to be the slope of our line. So 0.564, 564, 19.5 divided by 4.4. And we'll go, I'd say a reasonable rounding for that would be 2.5. Actually 2.500 we could go in terms of more decimal places in terms of writing it, but 2.5 will be good enough. So y hat is equal to a plus 2.5x. That's the slope. Now we need the y-intercept. What we're going to do is use the fact that the line has to pass through the average of the x's, average of the y's. So I'm going to plug into 107. Times 7. 175. Oh, that's not right. Didn't think that number was right. I lost my decimal point. I'm sorry. 2.5x. 2.5. That's why that number was making no sense. 2.5 times 7. 17.5. There we go. That makes much more sense. That's 89.5. And now we have a complete equation. Y hat is equal to 89.5 plus 2.5x. Now, as a couple of general reminders, if we're going to write a final answer on the AP exam and we're going to use the generic XY, we want to make sure that we specifically define what X and Y are. So in this case, I forgot what they represent. So X is grams of sugar. And Y is calories. The other thing you could do is incorporate those variables into the equation itself. That would also be acceptable as well. Slide this up out of the way. All right, second part. Calculate and interpret the coefficient of determination. Well, it's relatively common that they can give you R and ask you for R squared, or give you R squared and ask you for R. In this case, if R is equal to 0.564, R squared is 0.564 squared, which turns out to be about 31.8%. And our interpretation of that. About 31.8% of the variation. And then we want to put Y in context here, which is calories. Is accounted for or can be explained by. Either of those phrasings is okay. And then the linear model or the regression line, either of those phrases would be okay. And then relating Y to X, in this case you want to be back in context, relating calories to grams of sugar. All right, so let's recap real quick. This first handout, what's important? Reminder what the definition of a least squares regression line is, how the calculator calculates the correlation or the R value. A reminder how it appears and where it appears on your reference sheet. A couple of additional facts about lines of best fit that we haven't seen before. Those formulas appear on your reference sheet. The typical question that addresses this new material on the bottom, and then a set of steps in order to get it solved. All right, on to the second part of today's lesson. Here. Up top. An outlier is an observation that lies outside the overall pattern of other observations. Okay, that's general for any type of data set. In terms of scatter plots, points that are outliers in the y direction of a scatter plot have large regression residuals, but other outliers need not have large residuals. An observation is influential for a statistical calculation if moving it would markedly change the result of the calculation. Points that are outliers in the x direction of a scatter plot are often influential for the least squares regression line. All right, so outlier in the general sense is some data value that doesn't fit the overall pattern. Now, when we were doing a single list of one variable statistics, we had a specific rule to determine was something an outlier or not. We could do the 1.5 IQR rule. When it comes to scatter plots, there is no specific rule. It's more of a judgment call. These are some general trends that tend to happen. But not necessarily true for all single problems. So what we're going to do is run through, well, what are the steps that you can do to determine is a point influential or not, and talk about the gray areas in, well, can we call it influential or not. All right, so reading on the bottom, again, I apologize for this being blurry. The surest way to verify that a point is influential is to find a regression line both with and without the suspect point. If the line moves more than a small amount when a point is deleted, the point is influential. There is not a mathematical test to quantify markedly change the result of neither the calculation nor more than a small amount. All right, so here is the data set that we're going to use for this example. So I already have this in my calculator in the interest of time. Okay, what we're going to do is create a scatter plot for this data. And I'm just going to use a zoom 9 here for the purposes of time for this particular video. And we can see from the scatter plot here that we have a definite linear pattern and a point that definitely doesn't follow that linear pattern. So this point, by definition of what we're going to call an outlier for this particular topic, it's an outlier. It doesn't follow the overall pattern. This is not a gray area. That's a clear black and white. It is an outlier. Now, is that outlier influential or not? You can be an outlier and not be influential. So what we're going to need to do is to calculate a line of best fit with that, calculate a line of best fit without that, and then decide, well, is it enough to say that it's also influential? All right, so I'm going to go to Stat, Calc, Lin Reg. I'm going to put this in Y1, calculate, and I'm going to copy down the important stuff here. So our regression equation is y hat equal to, I'd say it's safe to round that to 3, plus, I'd say it's safe to round that to 0.5, x. Our r is about 0.816. Our r squared is about 0.666. What I'm going to do now is I am going to go to the graph, take a peek at what we have here. Now, the line of best fit in terms of how many data points do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Of the 11 data points, 10 of them all fall in this straight line. So the overall spirit of hitting 10 of the 11 points is the line should be there instead of here. That point is kind of tilting the line up this way. So let's see the numerical effect as far as how much of an influence is that having. So I'm going to hit trace. I'm going to go to that point and identify it. 1312.74. 1312.74. So that guy is definitely an outlier, yet to be determined is it influential. So I am going to go to Stat Edit, and I'm going to delete out that, make sure everything else still pairs up. 9 with the 7 point, nope, something went wrong. 10, 8, but we don't want the 13. I deleted out something incorrectly. 9, with the 7.11. And then we want 11, so let's delete out this. Does that line it up now? 10, 7.46, 8, 6.77. That should be gone. 9, 711, 11. Okay, now we're good. Okay, now I'm going to go back and rerun a line of best fit, except we will put it in Y2 and hit enter. So now our new line of best fit, safe to round that to 4 plus 0.345 x, our R is basically rounding to 1 now, to like 6 decimal places or something like that. Don't say it's exactly 1, because it's never exactly, well, in real world data it's never exactly 1. And let's take a peek. Alright, so with the outlier in there, the line of best fit was the blue. Without the outlier in there, the line of best fit was the red. Okay, so going back to an observation is influential for a statistical calculation if removing it would markedly change the result of the calculation. Okay, does that markedly change the line, shifting it from here to here? Well, it changed the y-intercept by 1, the slope by point whatever, and then got these guys to go almost perfectly to 1. I would say that it's safe to say that this is influential, that we markedly changed the calculation. And the other thing you can include in that, this is an older definition from a previous edition of the textbook. I believe that they also include markedly change the location of the line. So if you wanted to justify in a free response question, is it influential, you'd want to say it markedly changed the values of the slope, the y-intercept, the r and the r squared, and markedly change the location of the line. Okay, another type of question that they throw at you that involves this is they'll tell you a particular value is an outlier, or they'll tell you a particular value is influential. And then they'll say, what would happen if? And then it would be, that would be removed, what would be affected? So what you would need to do, I have this here that might be a little bit easier to look at, is if you know this is what it is before the outlier is removed, if you take that away without actually doing it on your calculator, what's going to change? What's going to remain the same? So you have to be able to visualize that taking that out is going to do this. It's going to tilt the line from there to there. So what changes when that occurs? Well, that y-intercept has to increase. The slope is going to get flatter. That has to decrease. That line is going to better fit the data, so these guys are going to get closer to 1, or potentially -1 if the data is going in the other direction. So, summary of the second handout here. Okay, number 1, reminding you of what the general definition of an outlier is. That outlier may or may not be influential. You can have outliers that if you remove them, doesn't do much to the calculations, doesn't do much to the location of the line. Okay, if it markedly changes the calculations or markedly changes the position of the line, then it's considered to be influential. Okay, these are some trends in terms of when and how they occur. I'm not a big fan of trying to memorize those. That's a very, very specific question. If you see that on the AP exam, highly unlikely that you're going to have to address what's in here. The more likely thing that you would have to do is to be able to make those types of predictions like I did here. If a point is removed, what changes, what stays the same, and then if you have to justify is it influential or not, it can be a judgment call. You can say that I believe that it has markedly changed. Or you can say I believe that the change was not significant enough to be able to classify it as an influential. As long as you reasonably back it up with solid vocabulary and use complete sentences and all the other good stuff when it comes to writing free response answers, you'll be given credit for that. All right, I think that wraps up what we need to know for today's lesson.